In this problem, we're going to find the volume of the solid formed by resolving the region that's bounded by the graphs of y equals x plus 2, so roughly this line, y equals x, which is this line, x equals 0, the y-axis, and x equals 3. So we're ultimately taking this space and revolving it around the x-axis. So picture-wise, really don't need to consider this stuff. And this stuff can be confusing as well, so I'm going to erase some of this excess. I'll do my best to draw this shape. It's probably going to look, so I've got this outside. It's going to look something like that, which means that this shape maybe has a circular component to it, and it always will because it's coming from a rotation, but there's a plug that's been taken out of the middle. So the principle is to find the area or the volume of the entire object with the plug and then subtract out the plug, and what's left will be the object we have. Right, so again, we'd like to find the volume of the entire shape and subtract the volume of the plug, right, the part that's being pulled out. Now, some things to notice. Our circles are still stacked, oriented horizontally, which means our limits of integration will be horizontal, and in this case, from 0 to 3. They're in terms of x. And we'll be integrating in terms of x dx. So that entire shape has a volume, and its volume will be found by integrating pi r squared, right, the area of the entire thing. Now the entire thing goes from the outside of the curve, and also I'll mark this in red. Right, so the entire thing is running from x plus 2 down to the x-axis. So the radius for our entire object, including the plug, is x plus 2 squared. And we're going to be subtracting out the plug. The plug also can be found thinking about it in terms of circles. And the radius of the plug, I'll do that in blue, is running from here to there. So its radius is just x. Not the best choice of blue. So we have first the entire object, its volume when we integrate, minus the volume of the plug, and the difference is the volume of the space left, the ring-shaped thing. Now a couple things that we'll do from here. Notice that we've squared each radius independent of one another. We can still treat this like one integral. I'm going to factor pi out because it's a constant, and I'll be integrating from 0 to 3. My outer radius minus my inner radius. And I can expand this if I wanted to. I could integrate by thinking about this in terms of the chain rule, right? There's lots of options as far as integration goes. The integral of x plus 2 squared is 1/3 x plus 2 cubed. The integral of x squared is 1/3 x cubed from 0 to 3. Now when I plug in my upper limit of integration, which is 3, this will be 5 cubed over 3, or 125 over 3, minus 3 cubed over 3, or 27 over 3, minus what I get when I put in my lower limit of integration, 0, which will be 8/3 minus 0. And 125/3 minus 27/3 minus another 8/3 would be 95/3. No, that's not right. 90/3. Right, because 90 plus 35 would be 125. And that simplifies down to 30 pi would be the volume of our object. This is sometimes referred to as the washer method because we're subtracting something out and our shape has a washer effect to it.